Ozonolysis of alkynes is carried by the cleavage of the triple bond. The reagent that we're going to use is ozone in presence of a peroxide. This is the only reagent that we're going to use for triple bond cleavage. And the presence of peroxide next to the ozone will make the ozone a strong oxidizing agent. So both ends of the triple bond will turn immediately into a carboxylic acid. The first thing that you would do with these problems is count the number of carbons that you are working with. So here I do have 5 carbons on the side. So draw your 5 carbons in there. This is 1, 2, 3, 4, and 5. Now the fifth carbon is going to turn into a carboxylic acid. So this is going to be my first fragment or my first half of the structure. And then my second part of the structure, count again the carbons. You have 1, 2, 3, and 4. So draw the 4 carbons. On the fourth carbon, you do have your carbonyl and the OH. Make sure at the end to count the total number of carbons and make sure that they are consistent with the number of carbons that you started with. So I have 5 on this side and 4 on the other side. This is 5 and this is 4. Now this alkyne over here is a terminal alkyne compared to an internal alkyne. And always terminal alkynes, whenever we want to break them, we are going to get carbonic acid since we have an acidic hydrogen over here, and this hydrogen will be oxidized into an OH. So count the number of carbons as I said, and you're going to end up having 1 carbon over here. So this is your carbon. You will end up having carbonic acid plus this is another carbon over here together with the cyclohexane. You have 2 carbons that are connected to the cycle. Carbonic acids, as we mentioned, they are kind of like unstable. So these are going to dissociate into carbon dioxide and water. So make sure to write down that these are going to be carbon dioxide and water. Ozone is a strong oxidizing agent that is going to cleave every single triple bond that we have in the structure. So start by counting your carbons, and every triple bond will turn into 2 carboxylic acids. So this is going to be 2 carbons. So you're going to end up having 2 carbons. On the second carbon, I'm going to have my first carboxylic acid fragment. And then this one is going to be 1, 2, 3, 4, 5, and 6. So I'm going to end up having a carboxylic acid on each end of this fragment. So this is going to be, draw your 6 carbons, 1, 2, 3, 4, 5, and 6. So on carbon number 6, I'm going to end up having a carboxylic acid. And on carbon number 1, I'm going to end up having a carboxylic acid. This way, you can easily see that these 2 carbons, they make a triple bond together. And then we have our last fragment, which is made up of 2 carbons. So I have here my 2 carbons as well, and then my carbonyl, and then my OH. So this over here, this fragment together with this fragment here make a triple bond with. Here I have a system of an alkene and an alkyne. Ozone in presence of peroxide will cleave both. This is a strong oxidizing agent. So the alkene, since it has 2 hydrogens in there, each hydrogen will turn into an OH. So each hydrogen over here, since it turns into an OH, you're going to get a carbonic acid, and that carbonic acid will turn into carbon dioxide and water. So I'm going to end up having these 3 fragments. So we're going to start with this one over here. You are going to end up having the carbonic acid, and that carbonic acid is going to turn into carbon dioxide and water. Plus the other fragment is 1, 2, 3, 4, 5, and 6. This is a branched fragment. So these are my 6 carbons. And it is a branched fragment on the second carbon. I would have one end of this fragment being a carboxylic acid and another end of that fragment being a carboxylic acid as well. 1, 2, 3, 4, 5, and 6. And then the last fragment is going to be 2 carbons. So these are my 2 carbons, and I'm going to end it with an OH in here. So this means that whenever you have something like this and you want to go backwards, put all the carboxylic acids next to each other and group each 2 carboxylic acids by making a triple bond. So these 2 carbons over here will make a triple bond, and these 2 carbons over here will make a triple bond. This carbonic acid is unstable, so it's going to turn into a carbon dioxide and water. The last reaction is the hydrogenation of alkynes, so meaning adding hydrogens to alkynes. There are 3 ways that you can add hydrogens to alkynes. You can change alkynes to alkanes by adding hydrogen in presence of PDC. Let's have an example. So if you have a triple bond, and you add hydrogen in presence of PDC. We know that PDC is a catalyst, and that is going to increase or speed the reaction. So I'm going to start by adding the first mole of the hydrogen in there, and the hydrogen will be added to both of these carbons. So I'm going to end up getting my cis alkene. But the thing about this reaction, so here I'm going to end up getting my cis alkene, and that is going to be my intermediate. The thing about this reaction is that it's unstoppable. I cannot stop it. And the reason why I cannot stop it because of the catalyst in there. So no need for me to say that I am adding 2 moles of hydrogen. It's already 2 moles of hydrogen that was going to add. So the triple bond is going to get hydrogenated until it turns into a single bond. It's going to pass by the alkene, and that is going to be the intermediate of the reaction. So that is going to be the intermediate of the reaction, but you cannot isolate it. So this means that I'm going to go ahead and add another mole of hydrogen in presence of PDC, and I'm going to end up getting my alkane in this case. So that's going to be 1, 2, 3, and 4. Stereochemistry doesn't matter in here because you have a rotation around the carbon, single bond carbon. Just make sure to count the carbons. These are 4 carbons. Put your 4 carbons in there and take the degree of unsaturation and make the bonds single bonds. The reaction goes straight from a triple bond to a single bond by simply using hydrogen in presence of PDC. I cannot isolate my alkene. If you wish to isolate now your alkene, you have to use a catalyst that decreases the reactivity of the hydrogen. And the catalyst that decreases the reactivity of the hydrogen is Lindlar catalyst. So that Lindlar catalyst here, instead of making the lead being absorbed on a charcoal surface, we make lead absorbed on calcium carbonate. And we decrease the reactivity of lead by coupling it with this bulky group in presence of quinoline solvent. All of those that you see, these are called Lindlar catalysts. Sometimes we show them like this, and sometimes we just write Lindlar catalyst. It's easier to write Lindlar catalyst, but if you see them above or underneath the arrow, just make sure that these are Lindlar catalysts. So all what they do is that they limit the reactivity of the hydrogen. So now instead of getting an alkane, I would isolate my cis alkene. So if I have an example over here, this is going to be my triple bond, and this is going to be my ethyl group, and I am doing hydrogen in presence of Lindler. Then in this case, I'm going to go ahead and isolate my cis alkene. So I'm going to end up having my cis alkene there. The reaction can stop here. It doesn't continue to an alkane because I limited now the reactivity of the lead catalyst. Now, I can also form the trans alkene, and those you are not responsible for the mechanism for those reactions by simply using sodium in presence of ammonia or lithium in presence of a deuterated ammonia. If I am using sodium in presence of ammonia, I would be adding two hydrogens that are trans with respect to each other. If I am using the deuterated ammonia, then I'm going to be adding the two deuterums that are trans with respect to each other. So let's have an example over here. We have our triple bond. So if I am using sodium in presence of NH3, then I'm going to isolate my trans alkene in this case. If I am using sodium in presence of ND3, then I am going to still isolate my trans alkene, but now instead of the hydrogens, I would be adding two deuterums. These reactions, we can use them in synthesis. So let's say, for example, if I'm starting with the propyne. Propyne is a 3-carbon alkyne, and I want to go ahead and synthesize a 7-carbon alkene. So I'm going from a double bond or a triple bond to a double bond. And I want to synthesize the E and the Z. The moment you see E and Z, this is a stereochemistry. So always remember that the last step of the reaction, because these are the only two reactions here, the Lindler and the sodium in presence of ammonia. These are the only two reactions that produce the cis and the trans or the E and the Z. So this means that the last reaction is going to be any one of those based on the stereochemistry that you need. So here I am starting with a 3-carbon triple bond, and I am ending up with a 7-carbon double bond. So I'm going to start first by alkylating the propyne to reach the 7-carbon, and then change the triple bond into a double bond. We're going to start, since propyne is a terminal alkyne. So I'm going to start with the hydrogen, the acidic hydrogen here, and I'm going to use a base as we did before. That base is going to come, take that acidic hydrogen, form the acetylide, and then I can use the primary alkyl halide since I have 3 carbons in here, and I want to reach a total of 7 carbons. So I would need an additional 4 carbons. So I'm going to end up using a primary alkyl halide with 4 carbons. This is an SN2 reaction. I would get my 7-carbon triple bond. Since I need the E isomer, I can go ahead and add sodium in presence of ammonia, and I would get the trans isomer. If I need the cis isomer, then I would use hydrogen in presence of Lindler. Another example involves the hydration reaction. So here I am starting with a 3-carbon alkyne, and I am ending up with a 4-carbon ketone. So the moment I see a carbonyl in there, I can go backwards and form my enol. In this case, since I am starting with a 3-carbon, I am assuming that the 3 carbons are those 3 carbons in here, and this alkene was my terminal triple bond. This means that I added 1 carbon. So to add 1 carbon, we are going to use the acidic hydrogen, use the base, take the acidic hydrogen, form the acetylide, and then use the methyl halide in order to get to the alkene. Now, once I get the alkene, since I have a symmetrical double bond, then it really doesn't matter if you add the OH here on this carbon or on the other carbon. So I can do either Markovnikov or anti-Markovnikov hydration. I can get my enol and I can do the tautomerization and get the keto. There are additional synthesis problems in the practice sheet, so please make sure you work those out.